Hello, so welcome. We will be starting a series called Course Overview where we'll be looking over our future projects or our current projects in under Omerco. So today we will be introducing our course on tropical geometry and machine learning. So tropical geometry is an extremely new field in math, and machine learning has been around since a couple years. And so what we'll be looking at today is a fusion between these two fields. So what is tropical geometry? Tropical geometry is a subset of a field called algebraic geometry, and in this field, what we study are the zeros of polynomials. What does that mean? That basically means solutions for anything with more than one variable. And we're interested in this because polynomials have obviously very wide range of applications. Almost quite literally anything you look at is has some sort of algebraic geometry associated with it. And the reason why tropical geometry is a subset of algebraic geometry is because algebraic geometry cares about what those solutions are. Tropical geometry says ki, okay, in the case where something is too complicated, how can we simplify to get some really basic or some really intuitive or easy to understand information. So what we're doing is we're compressing something really large and complicated into something small and simple. So what we do is we take our large and hard to solve polynomials, and what we do is we compress it into tropical polynomials, which are much easier to solve. Now, what we know is that polynomials are obviously going to be, especially higher dimensional polynomials, okay, say like 5-dimensional, 6-dimensional, and any dimensional. They're obviously going to be very complicated to even visualize, let alone solve. So, what tropical geometry does is it sort of squishes it down such that it is linear everywhere. So, what tropical geometry aims to do is it aims to linearize any given polynomial object. So what it does is you get something that looks like this, where each part over here, as you can see, it looks like a very pretty tiling, but in reality this is the tropicalization of a function. So what we do is we take our original polynomial and we translate it into the language of tropical polynomials, and then we study those to get some very basic and some really easy to understand properties. So this is here I'll be explaining how we typically go about it. So one of the most popular ways, not popular, it's the most easiest ways to go about converting a given curve into its tropical counterpart is called Maslov construction, and this is what's given here. What we do is we take our complex cubics, so we're assuming ki our variables are all complex valued, so this accounts for all solutions, yes? So what we're going to make is we're going to define something called an amoeba of a complex cubic. So amoeba, inspired by bio, it comes as a sort of webbish looking like thing. And what we do is we take, basically, if we have a variable and we have a polynomial with a given number of variables, instead of looking at the solutions of this polynomial, what we do is we take the log of each variable. So if you had x, y, and z, you're going to now be looking at the log of x, log of y, and log of z in the same polynomial. So you're going to substitute our log of x, log of y, and log of z into our original polynomial. And what we're going to do is we're going to take the base of our log. So we had log x, log y, and log z, but we haven't defined the base of any of them. We're going to take the base t over here, as you can see. Oh, my bad. Yeah, as you can see. And we're going to increase the size of our base so that it's extremely large. So what this does is it effectively does the same action of linearizing our polynomials. So we have the map z goes to log z, log to the base t of the modulus z. So this is a surjection of c. Basically, it goes into our original map. Okay, so there will be some variables that are not accounted for in the previous thing. So maybe two different z's mapped to the same log of z. So one example is if you had the variable z and you had the variable minus z. So the map over here will map to the same log to the base t of mod z, because mod removes the sign, right? So that's one very easy way to understand why it's a surjection. And what we do is we keep increasing the value of our base. We increase our value of t. Alright. And what happens is this, in some sense, oversimplifies our polynomial. So we can have an extremely complicated polynomial, say of 100 degrees or maybe lesser, something around that ballpark. So what it's going to do is it's going to basically forget any sort of details and like things like singularities, stuff like that. It's going to actually forget and compose into a super oversimplified version of itself. That is a tropical version. So what it does is it forgets the phase of z, forgets its angle, and then furthermore it rescales the norm so that every single thing oversimplifies completely. You lose all of this information. And then we may use log t to define operations on this. So what this does is it converts our whole polynomial into something very simple. So instead of having something of x into y into z, the fact that you're taking log, right, means that log of x, log of xy is equal to log of x plus log of y. So log is a kind of function that splits multiplication into addition, right? So if you had log of x into y, you make it into log of x plus log of y. So what this does is it completely simplifies a whole bunch of stuff. So we may introduce arithmetic operations such as a tropical plus or a tropical multiplication. And since log is not injective, we may have multivalued. Our function, our mapping may be multivalued. So I explained, right? Z and minus z may map to the same image in t, or yeah. I explained that's because we're taking log to the base t of mod z. So mod only converts both of these into the same image. So we may also see that, yes, this is what I meant by defining an addition. So you see x of y over here, right? Over here I've used off because PowerPoint does not support the circle with a plus thing, or like you could, I think if you've studied logic gates, you'll see XOR. So XOR symbol, the XOR symbol is not available on PowerPoint, so I cannot do that. Instead I've settled for O. So x of y is equal to log to the base t, the whole into t to the power of y, x plus t to the power of y. So this is how we define our new version of addition in this field of t. So we're mapping from C to T, right? So addition in C has now been converted into this kind of addition, where x of y is equal to log t to log to the base t into t to the power of x plus t to the power of y. Now what we do is what I said earlier, we have to go from this to this, right? So we have to go from this amoeba looking thing into this nice linear mesh like thing. So what do? We increase the value of t. So as t increases, our function converges into the mod. Yeah. So our function converges from this amoebic mess into the basically a whole bunch of max functions. So max of x naught y is equal to log to the base t into t to the power of x plus t to the power of y. And this expression has a good limit, has a well-defined limit. So as t goes to positive infinity, we have our addition well-defined, and recovering tropical addition is basically like a limit of this whole expression of log t, log to the base t into x, t to the power of x plus t to the power of y. So with the help of that, we kind of forgot the phase entirely, remember, because of this mod z over here. So now I'm going to tell you how this even applies to machine learning in the first place. So in machine learning, what we do is we take an error function, we graph that error function, we try to minimize that error function, right? So it's basically like you're defining a manifold, or you could say like a sheet, where the function is the sheet, and you're trying to find the points where it goes the lowest, so as to minimize that function. Or in other words, since I said it was an error function, we're trying to minimize our error. So sometimes, like I said, if we have a very high dimensional manifold, then it's going to be pretty complicated to solve. It could be. This is again an example of where we can apply tropical geometry. So what we do in this case is is that we take our manifold and we tropicalize it. So we completely turn it into this piecewise linear form, and we try to find new algorithms that can optimize this much faster. So the advantage is, because it's all piecewise linear everywhere, we love linear algebra, and linear algebra has time and time again shown that it has some of the most powerful tools. So we develop algorithms for that, and for at least for some basic models, it works pretty much just as good as the current models. So over here I've defined tropical spaces. Tropical spaces and tropical manifolds for our purposes is going to be pretty much the same. For someone more technically inclined, it might matter, the difference. But for an ML engineer, it's going to be pretty much the same. And what we're going to do is, you see this whole 3D mesh-like thing, right? This is basically our error function. So we're going to minimize this big thing, right? And finding the minimum of this is much easier, because you only have to look at the corner points of these, at the lowest corner point. So that already makes your job like much easier. You could do it visually if you like. And then you're gonna just see this, the corresponding point of this, in our original error function. And if it's good enough, then we settle for it. If not, we move on, because there's not that many points to check. There's a pretty countable number of points to check. So that helps us quite a bit. Now I'm going to tell you about the appeal of our program. You're going to learn R. So R is where we will be, because R is the standard for research in tropical geometry. So we will be learning to deploy ML models, and we will be learning to just apply whatever theory we have from tropical geometry onto current simple models. So we will be doing that. We will also be studying neural networks. And one thing I want to say is key, just by knowing about what tropical geometry is, and just by bringing that knowledge over to classical machine learning, you can probably attack some really good open problems that exist in the field. So what you're going to find, like right out of the box, you're going to be able to find applications in deep neural networks with piecewise linear functions this time. So neural networks already existed for quite a long time, but this time you're going to come with a tropical approach, and tropical geometry is a nice word to say. So you can come in with a tropical approach. You can completely linearize it, make a very simplified version of whatever they were doing already with sophisticated stuff. You can also go into probabilistic graphic models, which is a somewhat known field. And you can go into non-linear regression. So one thing that people are exploring is using neural networks that are of higher degrees. So, or they're using polynomial regression. So things like that are going to come in handy. So PWL stands for piecewise linear functions. And you're going to learn R, and you're going to make like working models that you can actively display on your own portfolios. So you can also be one of the first to actually even implement something like this, because tropical geometry itself is an extremely fresh field. So saying that you apply tropical geometry to say like a ReLU activation function, or quite literally anything with machine learning, because this is basically a tool to completely simplify anything you have. This is a tool to take any object, literally. It doesn't have to be ML also. It could be neural networks. You can have a tropical neuron, and you can define a neural network from tropical geometry, just using tropical addition, tropical multiplication everywhere you go. That's it. That's all you have to do. And you can start learning how to perform gradient descent on tropical manifolds, which is much easier, because like I said, all you have to look is for these individual corner points. And you may have your own discoveries. So you'll get a certification. You can even join us with a research membership. And so I urge you to check out our course. We will be uploading our courses on Udemy. And yes, go ahead. We have several courses. We have hands-on learning. We will teach you how to write research papers as well. And with that, I'd like to conclude. These are my contact details that I'd like to mention. I'm based in Bangalore. You can reach out to me whenever you like. And thank you for watching.